Welcome to the Explainer. So, if you work anywhere near modern data systems, well, you already know they can be absolute chaos. From failed pipelines to just painfully slow AI data loading, and of course, the frantic Slack messages that follow, the cracks are really starting to show in our foundation. Today, we're going to decode that chaos. We'll start with a structured framework to diagnose exactly where things break down, and then we're going to zero in on a cutting-edge storage technology that is quite literally rewriting the rules of performance. Okay, let's dive into this. We're taking a macro to micro journey today. We'll diagnose system chaos, cover the massive hardware paradigm shift, expose a legacy format bottleneck, dive into Vortex as the solution, and wrap up with some extreme performance benchmarks. All right, Section 1, Diagnosing Data System Chaos. When a modern data platform fails, the sheer complexity makes it incredibly difficult to pinpoint exactly why. It's like a giant puzzle. To find a shared diagnostic language for this, we can turn to the Datatism T6 framework. This is a vendor-neutral, highly structured model developed by researchers at Datatism.com. The guiding philosophy? A data problem without a dimension is an observation without a diagnosis. So the T7 model categorizes every single data failure across 7 distinct dimensions: truth, time, transformation, traceability, trust, technology, and team. For instance, if your data isn't reconciled, well, that's a T1 truth failure. Governance issues, that's a T5 trust failure. Now, what's really interesting about this slide is how we can categorize these dimensions. 6 of them are heavily rooted in human processes, logic, and organizational structures. But for us, we're going to funnel our focus entirely into the right side. T6, the technology dimension. This is the realm of systems, platforms, pipelines, and the raw underlying tools. And we're doing this because right now, deep inside that T6 layer, a massive bottleneck is choking the modern data stack. Which brings us to Section 2, the hardware paradigm shift. To understand why our T6 technology layer is struggling so much, we have to look at how drastically the bare metal hardware beneath it has flipped. Back in the 2010s big data era, we basically relied on homogeneous CPUs. You pretended a cluster of machines was one giant computer, right? And the immutable law of the land back then was that your PCIe bus was always faster than your network. Today, compute is wildly heterogeneous. It's totally driven by GPUs. And crucially, that speed hierarchy has completely inverted. On a modern cloud instance today, your network cards actually have about 8 times the bandwidth of the PCIe bus connecting to the GPU. So this shift brings us to the era of machine-scale outputs. 10 years ago, big data essentially meant taking terabytes of machine-scale inputs and distilling them down into human-scale outputs, like a dashboard that a human actually reads. But today, AI training requires taking terabytes per second and streaming them directly to a GPU. You just can't do that with legacy systems. You have to bypass those old constraints entirely. And that leads us to Section 3, the legacy format bottleneck. So, if hardware has evolved this rapidly, we have to ask, is our industry standard file format actually equipped for this new high-throughput reality? Well, according to Will Manning, he's the CEO of Spiral and the architect behind a new format called Vortex, the answer is a resounding no. As he pointed out in a recent Carnegie Mellon University seminar, Parquet is 12 years old. I mean, while it's absolutely fantastic compared to CSVs, it's become deeply calcified. Because there are dozens of different implementations out there, getting the whole industry to agree on changes is, as he puts it, borderline impossible. Let's actually look under the hood at Parquet's specific technical limitations at the T6 layer. First off, its metadata just wasn't optimized for modern object storage, which leads to high latency reads. Second, if you have a massive table, Parquet's overhead scales with the total number of columns you have, not just the ones you're actually trying to read. Third, it leans heavily on Z-standard for compression. Now, Z-standard offers great size reduction, sure, but it severely limits throughput, maxing out at maybe 1 to 2 gigabytes per second. And finally, tight data dependencies mean that if you want to pull a single random row for AI training, you often have to decompress an entire massive block just to get it. Enter Section 4. Vortex, the extensible solution. Because Tier 1 tech companies literally couldn't wait around for Parquet to evolve, they started building their own custom closed-source file formats. Vortex aims to stop that fragmentation in its tracks. Manning uses a really brilliant metaphor here, calling Vortex the LLVM for file formats. Just like LLVM completely revolutionized how compilers are built by creating an extensible harness, Vortex is an industrial-strength, highly extensible base layer. It's designed to be a future-proof harness for cutting-edge file format research, meaning new compression and encoding techniques can be plugged in effortlessly without breaking everything else. So the crucial point is how Vortex actually pulls this off, and we have to start with logical types. In systems like Apache Arrow, you have physical types, which basically means the system strictly defines the exact byte layout in memory. Vortex introduces logical types. This decouples the meaning of the data from its strict physical byte layout. This is huge because it allows for cascaded, ultra-lightweight compression that totally avoids those nasty data dependencies that slow Parquet down so much. Next up, we have arrays. Think of an array in Vortex as a mechanism to defer computation. So instead of immediately decompressing data to run an operation, an array holds the compressed bytes underneath and lets you just stack operations up. It effectively pushes compute down closer to the bare metal. It behaves almost like a logical query plan living right inside the file format itself. And to wrap up the core architecture, we have layouts. If arrays defer computation, layouts defer I/O. Layouts provide lazy data buffers that don't even have to live in memory. They make Vortex files almost entirely self-describing. This allows the system to intelligently evaluate and prune exactly what bytes need to be pulled from object storage, dodging those costly and unnecessary network reads. Let's move to and see how this builds an actual file. Vortex basically says goodbye to the rigid row groups you'd find in Parquet. Instead, a user provides a stream of arrays. Vortex then constructs pages that exceed 1 megabyte uncompressed. It buffers those pages into 2 megabyte flushed stripes, and then finally caps the whole file with a self-describing footer and a tiny postscript. This chunking strategy provides extreme flexibility, enabling just incredible locality and compression. All right, let's hit our final section, extreme performance and benchmarks. Architectural theory is great, right? But in the T6 technology layer, raw speed is literally all that matters. 137 times faster. That is the staggering speed increase Vortex delivers for random access reads compared to standard Z-standard compressed Parquet. Because of its lightweight encodings and a total lack of data dependencies, Vortex can effortlessly pluck specific rows out of a massive dataset without unpacking unnecessary junk. For AI data loading, this is a real game changer. But hey, it's not just about reading. Across a geometric mean of standard benchmark datasets, Vortex writes data roughly 5 times faster than Parquet. And when you need to do a full scan decompression and pass that data straight into Apache Arrow, Vortex performs that task a massive 18 times faster than legacy formats. And this brilliantly illustrates the current landscape for random access speeds. Parquet sets the baseline at 1x. Lance, which is a specialized custom format designed specifically for AI workloads, definitely improves on Parquet. But Vortex, it absolutely towers over both of them, delivering that incredible 137x performance multiplier. This speed has created a massive ripple effect across the whole ecosystem. I mean, Vortex is already proving to be an industrial-strength solution. It integrates seamlessly with Apache Arrow. Amazingly, querying Vortex files using DuckDB is actually faster than querying DuckDB's native file format. Dropping Vortex into Apache Spark yields a 30% reduction in query runtimes. It's twice as fast as Databricks' custom Mosaic format for streaming data to GPUs. And perhaps most importantly, its architecture allows for push-down orchestration, meaning the CPU handles the planning, but the actual data streams straight from the network card directly to the GPU. It entirely bypasses that slow PCIe bust we talked about earlier. We started this explainer looking at the Datatism T6 framework, mapping out the sheer chaos and complexity of modern data systems. We zeroed in on the T6 technology dimension and found a massive hardware shift colliding head-on with a 12-year-old file format bottleneck. But Vortex proves that by rethinking our foundational layers, embracing logical types, deferred compute, and extreme extensibility, we can unlock truly staggering performance gains. So I'll leave you with this question. If the hardware world has already leaped into the era of heterogeneous machine-scale outputs, how prepared is your stock to handle the transition? It might be time to run a diagnostic. Thanks so much for joining me on this explainer.